So this section, we're talking the zeros of a polynomial. The goal is to find the zeros of a polynomial. What a surprise. So a couple of recollections you have to make. Oh, did you notice how my little cart doesn't wobble too much anymore? Yeah, I fixed it. It took an Allen wrench is all it took. But I had to remember to bring it to school. Okay, let p of x be a polynomial function. Recall number one. The number c is a blank of p of x if and only if p of c equals 0. What do we call c if p of c equals 0? So what do we call c if p of c equals 0? We call it a, it begins with a z. I'll give you a hint. 0, there you go. But we spell it out, right? Because c itself it doesn't necessarily equal 0. It could, but it doesn't necessarily equal 0. We call it a 0 if you can plug it in for each input value in the formula that represents your polynomial and 0 pops out. Remember that? Number two, the real zeros of p of x correspond to x-intercepts. We talked about that a little bit, right? So does that make sense to you? As long as c is a real number, if you plug in p of c and get 0 popping out, that's the y value. That's 0, right? That's the p of x value or the y value that's 0. So what happens when y equals 0? Oh, the graph crosses the x-axis. Unless c is complex, then that doesn't correspond to anything in the xy plane. So that's important to realize. Here's a new definition. The number c is a 0 of blank if and only if x minus c to the k power is a factor of p of x. So if you can factor like p of x, but one of the factors repeats itself k times, that's how we think of it when you have an exponent of k on the factor. So x minus c is a factor. That automatically means c is a 0, right? If x minus c is a factor of p of x. Same thing with x minus c to like the 10th power. But we think of it as a repeated 0 10 times. So we call c, if the exponent is k in general, we call c a 0 of multiplicity k. A 0 of multiplicity k. Sounds like I just made that word up. Multiplicity k. The number c is a 0 of multiplicity k if and only if x minus c to the k power is a factor of p of x. So let's look at an example. Find the zeros of p of x and their multiplicities. So we have p of x equals x squared. It's factored for us. That's nice. X squared times quantity x minus 3 to the 4th times quantity x plus 1 to the 5th times quantity x minus 2 to the 10th. So what are the zeros? How do you get the zeros of a polynomial? It's just like finding x-intercepts. You set it equal to 0 and solve. Now, we could set each individual factor equal to 0, but I think you know by now that you get it by inspection since it's already factored for you and we're dealing with factors that are easy to work with. Just think of it this way. What could we plug in for x in the x squared factor and get 0 popping out for the whole thing? 0, right? Because if x is 0, then you multiply 0 times all these other factors, you get 0. So 0, okay, so let's make this correspond here. So 0 comes from the factor x squared, right? Okay, what 0, so that's a 0 that happens to equal 0, the number 0. What 0 do you get from the factor x minus 3 to the 4th? Yeah, just look. What could I plug in there to make that factor 0 and make everything 0 out? 3. What 0, Z-E-R-O, do you get from x plus 1 to the 5th? Negative 1. And from x minus 2 to the 10th? 2. So when it's in factored form, the zeros are easy to find. Oftentimes, you can find them by inspection. If it's not obvious, if you have a factor like 2/3 x minus 4 or something like that, then you could set the factor equal to 0 and solve in the usual method. Now, look at the exponents to get the multiplicities. What's the exponent associated with this the factor that gave you this 0, which is x squared. What's the exponent? 2. That's the multiplicity of that 0. So now you got it. So what's the multiplicity of 3? It came from this factor, x minus 3 to the 4th, so the exponent's 4. So 3 is a 0 of multiplicity 4. What about negative 1? Multiplicity is 5, corresponding with that exponent. And 2, 10. You got it. So really, we think of, for instance, 2 as a repeated 0 of p of x. It's a repeated 0 of p of x, and it's repeated 10 times. And that becomes important, especially in the next section. You'll see why. Okay. Everybody understands zeros and multiplicities? Yes?
So are the other ones repeated too?
Oh yeah. So 3 would be a 0 of multiplicity 4. So we think of two ways to think about it. You could think of x minus 3 as a repeated factor, right? 4 times. That's what it is, because that's what x minus 3 to the 4th means. But with that factor goes the 0 of 3, and we think of that as a repeated 0 four times. Okay. So this is a rational zero theorem. It's easy to use. It's user-friendly. Doesn't look like it when you read it the first time, but it is user-friendly. It would be hard to prove. You would prove this in an abstract algebra course. I know. So it's like a 400 level course. But we can use it. We don't have to prove it. The rational zero theorem, it's called. So p of x, remember the generic polynomial we invented the other day, the notation for that? So p of x is a polynomial of degree n, and you could specify that using the subscripts on the coefficients an x to the n plus an minus 1 x to the n minus 1 plus dot, 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 all the way till you get to the constant term. Okay, so what's the lead coefficient here? I need to make sure you understand what the lead coefficient here is before I read the zero theorem to you. What's the lead coefficient? The generic lead coefficient in this polynomial? If it's written in descending powers of x, which this is, the lead coefficient will actually be in the lead, won't it? So it's an. That's the lead coefficient. What's the constant coefficient? A naught. And it'll actually be on the other end, the right end, if it's written in descending powers of x. Okay, so suppose p of x is a polynomial function with integer coefficients. So integers are numbers like 1, 2, 3, 4, blah, 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 goes on forever. Also 0, negative 1, negative 2, negative 3, negative 4, blah, 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 goes on forever. So p of x is a polynomial, integer coefficients, and this is lowercase p divided by q. So this p here is not the same. This is uppercase p, not the same thing. So suppose p divided by q is a simplified rational zero. That's fancy talk. A simplified rational zero is a reduced fraction. A simplified rational number is a reduced fraction. So as opposed to 2/4, you're going to talk about 1/2, right? As opposed to 3/6, talk about 1/2. So suppose p divided by q is a simplified rational zero of p of x. Then p, it turns out, is a factor of the constant coefficient. And q is a factor of the lead coefficient. So p is a factor of a naught. Q is a factor of an. Sounds complicated when you read it in words, but in practice it's easy to use, because we use this theorem to identify the possible rational zeros of a polynomial, and our goal is to find the zeros of a polynomial. So what this will give us is like a list of suspects, a lineup of suspects, if you will. And some of them may be zeros. Not all of them will be. Sometimes none of them will be zeros. It only gives you rational zeros, possible rational zeros. So if there is a rational zero, it'll be in that list, and we have to find it. We have to whittle it away and figure out what the actual rational zeros are, and then we go from there. Go ahead.
Is that p over there on the bottom left corner, is that the lowercase p?
Yeah. Okay, so in this example, we're going to, let me move this just a bit. In this example, we're going to find the zeros, state the multiplicities. I'm only going to state the multiplicities if they're different than 1. If it's a multiplicity of 1, I'm not going to bother. So first polynomial, p of x equals 2x cubed plus x squared minus 18x minus 9. Okay, so first of all, list, what I want you to do is I want you to list the factors of a naught. What is a naught in this case? So a naught is the constant term. What's a naught? Technically it's negative 9, right? So I want you to go ahead and we're going to find the possible rational zeros using the rational zero theorem. I want you to list the factors of a naught, which is negative 9. So what are okay, plus or minus works on each one, so here's what we can do. Go plus or minus, and then list the absolute values. You don't have to worry about plus or minus on each one. After the curly bracket, list the absolute value of all the factors, negative 9. So just think 9. What are the factors of 9? Start with 1. 1, 3, 9. Plus or minus on all of them, and you can put that out in front so you don't have to write plus or minus 1, plus or minus 3, plus or minus 9. Although if that's how you want to do it, you can do it that way. Okay? What are the factors of an? In fact, what is n in this case? What's the degree of the polynomial? Factors of a3. Again, that's an because n is 3. Oh, that's not too bad. What is a3 equal to? What is the lead coefficient? 2 is a prime number. So, disregarding the plus or minus, how many, for a prime number, how many factors does a prime number have? 2. 1 and itself, right? So 1 and 2. But we do have to put the plus or minus on both of them, so there's actually 4 numbers there. Plus or minus 1, plus or minus 2. Okay, so what the rational zero theorem says is any fraction formed with one of these guys, everybody look up. Any fraction formed with one of these guys is the numerator, and one of these guys, including the plus or minus, so let me amend that. One of these guys, so there's really 6 possibilities there. Plus or minus 1, plus or minus 3, plus or minus 9. So any fraction formed with one of those guys as the numerator and one of these guys as the denominator is a possible rational zero. That's the rational zero theorem. That's all it says. And there's a finite number of them, and there's not that many of them. We can just list them all. So let's do that. Let's call them PRZs for short. Possible rational zeros. So here's how I like to do it. Put the plus or minus on the outside of a set list, so curly bracket, and just take one. Now, which one am I referring to? I'm referring to the one from the factors of negative 9. And make all the fractions you can with 1 in the numerator and 1 or 2 in the denominator. There's only 2 possibilities. You could have 1 divided by 1, which is 1. Or what's the other one? 1 divided by 2, 1/2. So those are the possible rational zeros with the plus or minus in front. Those are all the possible ones with 1 in the numerator. So let's go to 3. Let's go to this 3 right here and form all the fractions with 3 in the numerator. There's only 2. Well, if you disregard the plus or minus, there's only 2. 3 over 1 and 3 over 2. We've exhausted all the possibilities with 3 in the numerator, so what's the last 2? 9 in the numerator. 9 over 1, which is 9, 9 over 2. Those are your possible rational zeros. That's your list of suspects. Sure, why not? So it's your list of suspects. How do we narrow down so we don't have to use, I don't want to plug each one of these in or use synthetic division on each one of these to evaluate p of x and see if we get 0. So is there a way to whittle it down? Yeah, you use the calculator. because these will show up as x-intercepts. Technically, an x-intercept is a point, but they correspond with x-intercepts if you look at a graph. So we're going to take advantage of the technology. Pull out your graphing calculator. Oh, let me put it over here. Put this down here. So remember what the list looks like. You know what I'll do? I'll move this down here so we can see it. Okay, so here's your calculator. Let's go to y equals and type in the polynomial. Let me move that for a second. The polynomial is 2x cubed plus x squared. Oh, darn it. I hate it when I do that. There we go. Got to get out of that exponent. Plus x squared minus 18x minus 9. Double check. Make sure you typed it in right. Okay. Then go to zoom number 6. That'll put it on a standard screen from -10 to 10. I don't see the peaks and the valleys, do I? But I don't care. I'm just looking for x-intercepts. Okay, so look at our list of possible rational zeros, plus or minus on all of these. And then look on the graph where it appears the x-intercepts occur, the x values of the x-intercepts. So where does it appear this first x-intercept is at? -3. You could actually plug if you hit trace first, plug -3 in the calculator, and it will evaluate the polynomial at -3. You can see 0, in fact, does pop out. So here's what you're going to have to do, though. You can't rely, as you'll see, you can't rely totally on the calculator to find zeros for you. So we're going to verify that -3 is a 0, not by direct substitution, but by synthetic division, the remainder theorem, because the remainder upon division by x plus 3 will be 0. And in fact, the remainder theorem tells us that the remainder will be p of -3 when you divide by x plus 3. So here we go. Let's do that.
Do we have to divide each possible zero?
Well, we'll talk about it. So let's start. And by the way, pay attention to the form of what I'm doing too, because this is going to be a nice sleek way to do it. So we're going to put -3 up in the corner. This is the synthetic division that we've already learned. -3 up in the corner. Look at p of x. Make sure it's in descending powers of x. Make sure there's no power of x missing. And as long as there isn't, just write down the coefficients from left to right. So what are the coefficients? 2, 1, -18, -9. Now, when you do this division, you fully expect the remainder to be 0. Okay? If you don't get 0, something's wrong. Okay, so let me bring down the 2. What do I do with the 2? Get -6. What do I get when I add these together? -5 multiplied by -3. Negative or positive? 15. Add them up. What do you get? -3 times -3. Positive 9. You add them up. You get 0, as you expected. So you just verified. Now, let me remind you what the remainder theorem says. The remainder theorem says that this remainder, R, is equal to P of the value up in the corner we call C. It's equal to P of C, right? Which is P of -3. So you just verified that P of -3 equals 0, right? That's the remainder theorem. That's a lot faster than plugging it in by hand and going 2 times -3 cubed plus -3 squared minus 18 times 3 minus 9. This is way, by several factors. This is way, by 3 or 4 times, this is way faster doing it, synthetic division. It's almost as fast as the time it takes to pull out your calculator and do it. It's almost as fast as the calculator. When you're dealing with fairly nice numbers. What was another 0?
1/2.
Positive or negative?
Negative.
Looks like -1/2. So here's a big point that a lot of students miss. Okay, what's the coefficient that we have left over from the synthetic division we just did? We started out with degree 3. So what would the quotient actually be right here? 2, I'm going to erase this in a second, but I want to make a point here. 2x to the second power minus 5x minus 3. This quotient contains the remaining factors of p of x, which means it contains the remaining zeros. So to verify that, for instance, negative 1/2 is a 0, we're going to plug it into the quotient and not the original polynomial. And if since this quotient is a factor of p of x, does everybody get that? Look, you could factor p of, I'm going to erase this in a second, but I just need to make sure you understand this. By the check on division, since the remainder is 0, you could factor p of x as this quotient times the divisor, which was actually x plus 3. If c is negative 3, the divisor is actually x plus 3. So p of x factors to involve this quotient, which means any 0 of p of x will be a 0 of this quotient. Is that clear? So instead of concentrating on the more complicated degree 3 polynomial we were given, we can concentrate on this degree 2 quotient. And you could factor it or use the quadratic formula on it, but here's a slicker way to do it. You're pretty darn sure that negative 1/2 is going to be a 0. So just continue the synthetic division like this on those coefficients that you already have written down from the division you already did. So put negative 1/2 to the left of those coefficients from the quotient, and then start that synthetic division process all over again. Bring down the 2. What's negative 1/2 times 2? Negative 1, add them up. Negative 6 times negative 1/2. Positive 3, and you fully expect to get a 0 remainder, and you do. Now, what quotient is left? 2 and the negative 6 go with a degree. So these coefficients went with a degree 2 polynomial. These coefficients will go with a degree 1 polynomial. So I suppose you could say the coefficient, don't write this down, 2x minus 6 is the quotient that's left. And that will be a factor of p of x also. So if you wanted the 0 of that, you could just set it equal to 0 and solve. Add 6, divide by 2, get 3. But there's a slicker way to do it. At least in my mind, it's slicker. You already know from that picture on the calculator, so I'm erasing this. From that picture on the calculator, hold on, my calculator went to sleep for some reason. From that picture on the calculator, you're already pretty sure that, okay, what's this 0 going to be? 3. You're already pretty sure the next 0 is 3. So let's use synthetic division one more time. It's super quick. 3 up in the corner, but this time on the quotient you got from the last division, the coefficients of which are 2 and negative 6. And do the process one more time. It'll be 2 steps. Bring down the 2. I suppose it's 3 steps. 2 times 3 is 6. Add them up, you get 0. So you just verified, since you got a remainder, three different remainders of 0, you just verified that those 3 numbers are zeros of the polynomial, Z-E-R-O, right? They're not the number 0. So what are the zeros? You could state your answer like this. You could say the zeros are, you could say plus or minus 3 if you like, comma, negative 1/2. Or negative 1/2, comma, plus or minus 3. Doesn't matter. Now, they're all multiplicity 1, so I didn't state that. You didn't have any repeated zeros there. You'll know what I mean in a minute when we get a repeated 0. You'll know what it looks like in a minute. Question?
It almost seems like without putting every positive and negative value you have in that list, you basically could not do this without a calculator.
Oh, well, it's interesting you brought that up. Back in my day, kids, I actually had a TI-81, but I had no idea how to use it to what we're doing right now to find the zeros. And it would have worked, actually, to do most of what we do. But I didn't know how to use it. So back in my day, what did we have to do? Yeah, well, not all. Hopefully you got lucky, right? If you got lucky and got it down to a quadratic factor, then you could either factor it and use the quadratic formula on it real quick, right? So you've got it down to a quadratic quotient, then you can set that equal to 0 and solve that for the remaining zeros. But yeah, I had to do a whole lot of synthetic division where I didn't get 0 as the remainder, so I had to try something else. Now, there is a rule called Descartes' rule of signs that can narrow down the number of rational zeros. There's also something called the upper and lower bound theorem. You can read about them if you want. I don't talk about them. I don't even remember them anymore. I haven't talked about them in so long because the calculator have made those laws obsolete. But yeah, it was harder. So yeah, I had to walk to school uphill to Palomar College. Both ways uphill back then. It was in the snow too. And we didn't have these fancy graphing calculators helping us. You guys got it easy. All right. Part B, same directions, find the zeros. Now, the whole thing about finding the possible rational zeros is no problem here, because look, what's A naught? 1. What's AN, which is A3 in this case? So do I have to go through that whole process where I put the where I put the factors of A naught over individual factors of A3, the lead coefficient, to find the possible rational zeros? They're both 1, right? So the PRZs, technically you got to throw a plus or minus in there. The PRZs, there's 2 of them. You don't need the set brackets, just plus or minus 1. So that's not a big deal. And furthermore, you can tell which one works just by inspection. You could plug that in your head if you thought about it. You know, there's 2 numbers, 1, -1. Which one's going to make 0 when you plug it in? 1, right? Think about it. You cube 1, you get 1. Minus 2 times 1, you get -2. Add 1. Yeah, you add those numbers together, you're going to get 0. But -1 won't work because when you cube it, you'll have that negative will stick around.
Well, and -2 turns into a +2, and then if
So the point is -1 won't work, but +1 will. No calculator needed, right? Here's the thing. If we do graph it on the calculator, something weird is going to happen. So you still, even though you identified the rational zero, the one rational zero that works right away, which is 1, it's still worthwhile to graph it. And you'll see why as soon as we do it. So x cubed minus 2x and then plus 1. Let's graph it on the standard screen. Zoom number 6. Okay. Now wait a minute. What's happening right here? Is that 1, 0 right there?
yeah.
It's kind of hard to tell, but it looks like something funky might be happening right there. Zoom in on it. I'm moving the cursor near where that 0 is. Oh, do you see? It's actually, let me get the cursor out of the way. It's actually a couple of different zeros right there. The one we just found is right here, right? But there's one right here, and there's one right here. But they didn't show up in our list of possible rational zeros, did they?
No.
Means they're irrational. They're not complex because complex numbers won't show up at all. It means they're irrational, and that possible rational zero theorem doesn't do us a bit of good. Now, the calculator does do some sophisticated numerical calculations, and you could find a decimal approximation of those zeros. But we could also find exact values, which is nice. So let me show you how we could find the exact values of those remaining zeros. You're going to have to go ahead and do synthetic division on the one number you know to be a 0. 1. Using the one number you know to be a 0, do the synthetic division. Not because we know the answer. When we look at the remainder upon division, or if we plug in 1 manually, we're going to get 0. So we know 1 is a 0. But we're using this to get the quotient upon division by x minus 1 into p of x. Okay, so careful here. What should the coefficients be? You got to be careful. It goes from 3, a power of 3 to a power of 1. So you got to kind of put a plus 0x. Well, let me write it out. That looks terrible. So let me write it out. You got to write it out as x cubed plus 0x squared. It skips over x squared. Minus 2x plus 1. And then you can see all the coefficients. So 1, and then you got to plug in 0, and then minus 2, negative 2, and then 1. If you don't put in that placeholder 0, it's not going to work out good. Okay, bring down the 1. 1 times 1 is 1. Add them up. 1. 1 times 1 is 1 plus negative 2. Negative 1 times 1. Negative 1, we do get 0. I already knew that. I'm after the quotient. Can you write down the quotient based on those coefficients we just got? We started with the degree 3, so the quotient, when you divide by a linear polynomial like x minus 1, the quotient will be 1 degree down from the polynomial we started with. So what's the polynomial we're looking at here? What's the quotient? X squared plus x minus 1. Does everybody see how we got that? So this quotient will contain the remaining factors of p of x, which will contain the remaining zeros of p of x. So what do? Well, we set it equal to 0, and we solve. Because we don't... Why does it keep doing that? No. Let me just turn down the sound. Okay. So... we don't have any other suspect zeros, do we? We don't. In other words, we don't know what those other ones are, so we can't use synthetic division here on unknown things to plug in, on unknown numbers. So the good news is x squared plus x minus 1 is quadratic, and if we set it equal to 0, we know how to solve any quadratic equation in the universe. I don't think we can factor it, but what can we use? The good old quadratic formula. If you have ax squared plus bx plus c equals 0, a, b, and c are constants, what's the quadratic formula say?
X equals negative opposite b plus or minus the square root b squared minus 4ac all over 2a.
That is correct. Okay, so we're going to use the quadratic formula. What's a, b, and c? 1, 1, negative 1, right? In order. So what do we get? We get x equals, fill it in for me. Negative 1 plus minus. 1 squared is 1 minus 4ac. A is 1. C is negative 1. That's important. Otherwise, you're going to get complex solutions when they're not really there. Over 2 times a, 2 times 1. So what are you going to get underneath that radical?
2.
You're going to get 5, right? So this will be a plus 4 when the dust settles. So 1 plus 4, 5. So negative 1 plus or minus root 5 over 2. There's 2 zeros right there because of the plus or minus. So your zeros are 1, and then you can write 2 and 1 by just going negative 1 plus minus root 5 over 2. So here are your zeros. They're both or all 3 of them actually, since there's 3 there. They're all multiplicity 1. I'll show you in the next example how to handle a greater multiplicity. Is that clear how I did that? Got it down to a quadratic quotient and then used usual techniques, set it equal to 0, used the usual techniques to solve. If it factored, great. But if it had factored, then you would have those zeros would have probably shown up as rational zeros. Questions? All right, let's try another one. Part C, p of x equals 4x to the 4th minus 4x cubed plus 13x squared minus 12x plus 3. Ooh. Yeah. Okay. Start by using the possible rational zero theorem. What is A naught in this case? I want you to list. By the way, when you list the possible rational zeros, if you get repeats, don't list them twice. And that could happen. You can get like 3/4 and 6/8. 6/8 reduces to 3/4, so don't list it twice. List the reduced fractions only, and no repeaters. So factors of, okay, a naught is equal to 3. That's pretty easy because it's prime. Plus or minus, what are the two factors of 3? 1 and 3. Okay, and then the factors of, what's n in this case? The degree is n. N is, what's n? This 4 right here, right? So A4 is 4. What are the factors of 4? Plus or minus 1, 2, 4. Okay, so list the PRZs by forming all the fractions you can with either 1 or 3 in the numerator, plus or minus on all of them, and one of these, 1, 2, or 4 in the denominator. So what are the possible rational zeros? I'll get you started. 1 over 1, so just 1. What's the next one if you leave 1 in the numerator? 1 over 2, 1 over 4. That exhausts possibilities with 1 in the numerator. So go to 3. So put 3 in the numerator. You could have what? 3 over 1, right? Which is 3. 3 over 2 or 3 over 4. So in the homework, you're going to do this whenever it's practical. I think there's one example where it's not practical to list them all. You're going to have to use other clever techniques to solve it. But in the vast majority of the homework problems, you're going to want to list your possible rational zeros. Do it just like I'm doing it here. Okay? But again, if you have like 50 of them, it's not practical. Don't try to do it. Okay? There's going to be another clever way to work the problem. Those are our prime suspects. Let's narrow down the list of prime suspects by graphing this thing. Okay, so 4x to the 4th minus 4. Darn it, I did it again. Minus 4x cubed. Got to get out of that exponent. Plus 13x squared. Minus 12x. Plus 3, double check it. It's easy to make a mistake on my virtual calculator. Okay, so let's go to zoom number 6, see what we can see. Whoa. Huh. It doesn't have to be quadratic. In fact, it's not. It's quartic. 4x to the 4th. Well, okay. It looks like there's a 0 there. We could zoom in to be sure. Make sure nothing funny is happening there. Yeah, what does it appear to be?
1/2.
You could check, hit trace, plug in 0.5, 1/2. And you do get y equals 0 popping out right there. So it works. Has a kind of a bouncy behavior at that x-intercept, doesn't it? That's worth noting. We'll talk about that in a second. Okay, so that's the only, out of our prime suspects, 1/2 is the only one that looks like it might work. So let's do synthetic division on that. So here we go. Let me shrink this stuff down. Get it out of the way. Okay, so 1/2 up in the corner. I think if you scan p of x, it goes down in descending powers of x each term, and I don't think there's anything missing. So 1/2 in the corner. What goes across? 4, -4, 13, -12, 3. What do we fully expect to get for the remainder? 0. I'm going to write it down ahead of time. If you don't get 0, you're pretty darn sure you did something wrong in the synthetic division, right? You got to go back and check. But that's the good news, right? You know what you're going to get ahead of time. Okay, you guys do this for me. I'm going to get you started, then you do the rest. Bring down the 4. What goes underneath the negative 4? 2. 4 times 1/2. 2. So add them up. Negative 2 times 1/2. Plus 13. Times 1/2. Plus negative 12, negative 6. Times 1/2. Add them up. 0. All right. So those coefficients correspond to a degree what polynomial for the quotient? 3. So I don't want to write down the quotient and set it equal to 0 because I don't necessarily know how to solve a degree 3 equation. Maybe we could factor it, maybe by grouping or something. But there's a better way. Because of the bouncy behavior, so take another look at the graph. Because of the bouncy behavior at the x-intercept, which corresponds to the 0, we know that the factor associated with that x-intercept has even degree, even multiplicity, using the language we developed for this section. Remember that? Bouncy behavior corresponds with even exponents on the corresponding factors. So what does that mean? So what's the factor if you were to factor p of x? One of the factors could be x minus 1/2, right? X minus the 0, which is 1/2. That's the factor theorem. But it's not to the first power. It'd have to be either to the 4th power or more likely to the 2nd power, right? Because of the bouncy behavior at the intercept, it's probably going to be it's got to be to an even power. X minus 1/2 to an even power, probably 2. It could be 4. You're going to find out in the next section that you can have as many zeros as there is multiplicity. In fact, if you include multiplicity, let me restate that. I said that wrong. You can have as many zeros as the degree. The degree is 4 if you include multiplicities. That's part of the fundamental theorem of algebra. You're going to discover that in the next section. So long story short, the multiplicity on that factor could be 2 or 4. So you could think of 1/2 as a repeated 0. Okay? So what does that mean? Well, that means we can do the division one more time. In other words, we can plug in 1/2 one more time and expect, do the synthetic division on the quotient and expect to get 0 again. So let's do that. And why are we doing the division again? Because the next quotient down will be degree 2, won't it? Because we're doing the division on the quotient, which was degree 3. So bring down the 4 times 1/2. What do you get? Add them up. Negative 2 plus 2? 0 times 1/2 plus 12 times 1/2 plus negative 6. 0. Okay, so this 4, 0, 12, these coefficients are the coefficients of a quadratic quotient. So what would that quadratic quotient be? 4x squared just plus 0x, right? So we don't write that down, plus 12. The remaining zeros of p of x will be contained in this factor. So let's set it equal to 0 and solve it. So what's the best way to solve that one? Could use the quadratic formula, but that's like trying to kill a housefly with a shotgun. Don't need it. And it might make a mess. In fact, you could count on it making a mess. You could get it right, though. It would work. How about, because there's a single x squared term and no x to the first power term, we could solve it by taking roots, couldn't we? Couldn't you subtract 12 from both sides, divide by 4, isolate the x squared? So if you subtracted 12 from both sides, don't you get 4x squared equals negative 12? Divide both sides by 4, what do you get? X squared equals negative 3. And once you isolate the x squared, you can solve by taking roots, square roots of both sides. Now, what do you get when you take so you have x squared equals negative 3. You take the square root of both sides. What do you have to remember in front of the square root? Plus or minus. What is the square root of negative 3? If you simplify it using the techniques we developed previously, what do you poke out? you poke an eye out. So it's I root 3 plus or minus in front. No wonder why it didn't show up on the calculator. Complex numbers don't show up in the real xy plane. They never do. So these are two zeros that are not corresponding with any x-intercepts. But you could still plug these values into the polynomial, either use synthetic division or plug them in directly, and you'll get 0 popping out if you do it right. So what are your 4 zeros?
1/2.
Let's write down the multiplicity. 1/2 is repeated, right? So 1/2 in parentheses, let's put multiplicity 2, comma, plus or minus I root 3. Okay? Yes?
If you had a different C value in the, like in the first one that you're doing synthetic division on, would you just do it on the same number again? Like try to
I don't think I understand the question. What? So if you had a different C value than what? Than 1/2? If I had that behavior, the bouncy behavior on the graph at that C value when you graph it, yeah, I would. Yeah, anytime you get bouncy behavior or curvy behavior. So if you get some of the earlier graphs, if you look at like the first one, all these zeros were multiplicity 1, right? So if you go back, I don't want to regraph it, but if you go back and look at the 0 there, I don't remember if it was going up or down, but let's just, for the sake of argument, say it looked like that, and that 0 was -3. It looks, if you zoom in on it, it looks like a straight line there when it's a multiplicity 1. But if you get curvy behavior at the x-intercept, like that, that's an indicator of a high odd multiplicity. You get bouncy behavior, even multiplicity. You get curvy behavior, it's odd multiplicity. But if it's a straight line, then it's probably multiplicity 1. If it curves and bends, it's probably multiplicity 3 or 5. I don't think you'll see very many problems where you get 5 repeated zeros, but you could. You would check it again. It's a good indicator on the calculator you've got repeated zeros. Yep. And you would want to, if you think you have, so if you have that curvy behavior, you have at least 3 zeros, you'd want to do the division 3 times with the same number. Does that make sense? In other words, plug in the same number 3 times. So since we're here, what if you were asked to, I don't remember if I did this last time, I don't think I did. So what if you were asked to factor P of x? So you know the zeros, you know these are the zeros. -3, -1/2, +3. What if you were asked to factor P of x? Could you do it? What are 3 factors of P of x? Let's write them down. And we'll say we'll be wrong at first, but let's say P of x equals the 3 factors multiplied together. So zeros go with factors. So what's the corresponding 0 with, let's start with +3. What's the zero that corresponds, what's the factor rather, that corresponds with a 0 of +3? X minus 3. That's from the factor theorem, right? So if 3 is a 0, x minus 3 is a factor of P of x. If 3 is a 0 of P of x. What's the factor that goes with x plus 3? I'm sorry. It must be Friday. What's the factor that goes with a 0 of -3?
3.
X plus 3. I stated the answer in the question. What's the factor that goes with a 0 of -3? You go x minus a -3, right? Which is x plus 3. You always just take x minus c if c is the 0. So what's the 0 that goes with -1/2? Gosh, I did it again. What's the factor that goes with -1/2? What's the factor that goes with a 0? That's the 0, right? Of -1/2. X minus a -1/2, which is x plus 1/2. All right. Sometimes your vocal cords won't do what your brain tells it to do. There we go. That is wrong. That is not the factored form of P of x. It has the same factors of P of x, but it's not equal to P of x. How do I know that? What would be the lead coefficient if you were going to, or the lead term if you were going to multiply it out? To get the lead term, all you have to do is multiply out the lead numbers in each factor. It would be x times x times x, which is x cubed. Look at p of x. What's the lead term? 2. It's off by a factor of 2. So all you have to do to get the factored form of p of x is put a 2 in front of these factors you just listed. Now, you can be sure that if you were to multiply this out, you would get the original p of x with the right lead coefficient and everything. Okay? Now, that's up to a constant, and there is something else you could do with that too. If you don't like the plus 1/2, you could distribute this 2 to any one of these factors that you want. You don't distribute the 2 to more than one factor. But let's say you wanted to distribute the 2 to this factor. That would have the effect, you'd still have x minus 3, you'd still have x plus 3. But what would it do if you distributed a 2 to this factor? You'd have 2x plus 1. So you got to be aware of little variations like that. That would also be a valid factorization of p of x. Okay? So by finding these zeros, we can factor the polynomial linearly. If we find all the zeros, all those factors will be linear factors. Okay. Any questions on how I did that factorization? WebAssign, just be aware of the instructions. I think on some of the problems they'll say if you have a repeated 0, you just list it as many times as it's repeated. So in that last problem, you'd list 1/2 twice, separated by a comma.